I'll read the title. So I'll talk to you about Lagrangian Cobordisms between Legendrian Submanifolds. Everything I say today is joint with Lisa Traynor. A lot of what I say today is also joint with Frederic Bourgeois. I will try to distinguish between the two. I'm sure Frederic won't mind if you just attribute everything to him anyway. I want to split the talk into three segments. Segment number one, I'll give you some basic definitions and a little bit about some questions one might try to ask and answer in this field. Then I'll talk about constructions of Lagrangian Cobordisms and therefore be able to talk a little bit about the smooth forginess of a knot. And then I'll talk about how Lagrangian Cobordisms and Legendrian Submanifolds sort of are the geometry underlying TQFT package for a non-classical invariant of Legendrian Submanifolds. This, of course, works for many different kinds of non-classical invariants. I'll talk about generating family cohomology today. Okay, so let's get started. And let's talk about the following. So I want to work in the standard contact R2n plus 1. Of course, many of my pictures will be in R3, but everything I say generalizes just fine to higher dimensions. And in fact, I'm really not going to write this down. Everything I say generalizes just fine to the one jet space of any compact manifold. With its standard contact structure, and I want to look at Legendrian submanifolds inside the standard contact space. In other words, I want to look at n-dimensional submanifolds whose tangent space lies inside of the contact structure. And it's useful to be able to visualize these things. So let me get and today, there's a step here. Ladies and gentlemen, I'm going to sue the University of Georgia by the end of today.
Visualize that.
See?
Visualize.
I will now visualize the step and also visualize Legendrian submanifolds via their front projections or the projections to their xz coordinates. Okay, so let me just draw a couple of those. I'll draw one in R3, and I'll also try to draw one in R5. I will not try to draw one in R7. All right, so here's an example. Okay, so this is a front projection of a Legendrian twist knot in twist knot in R3. The features to notice. Oh, well, okay, that was too quick. That there are no vertical tangencies, only cusps. And also that you can recover the y coordinate just from the slope of the x from the slope in the x projection. And in R5, with sort of the same kind of things hold, where we won't have any vertical tangents, only cusps. Maybe this time we'll have circles of cusps. And again, you can recover the y coordinates just by taking derivatives of the xz slopes. So, because this is the flying saucer. So now we have sort of circles of cusps. And we could have higher singularities as well, but I really don't want to bother drawing those. Okay, and at least initially we want to think about these. Want to think about these things as sort of trying to work with them up to isotopy through other Legendrian submanifolds. Okay, but there's when we do that, by the way, there's sort of one classical invariant that I want to use today. And that's just the Thurston-Benneken number, which today I'll just think about as take your Legendrian submanifold, shift it off itself in a direction transverse to the contact structure, vertical is just fine, and then take the linking number between the Legendrian and its vertical push-off. All right, so, but another relation that we can try to impose is maybe something a little bit, well, perhaps, well, actually something that's definitely weaker. And that relation would be the relation that you get from Lagrangian Cobordism between Legendrian submanifolds. And let me just say exactly what I mean by that. So we'll say that the Legendrian submanifold lambda minus is coborded to the Legendrian submanifold lambda plus via a Lagrangian L. If there exists, not for all, but if there exists a submanifold inside this symplectization of our standard contact space, so that, well, and we want this to be an exact Lagrangian. The Lagrangian condition, of course, just means that if we take the symplectic form and we restrict it to the tangent bundle of Lagrangian, it vanishes. Exact, well, if you know what it means, great. If you don't know what it means, it's not really going to come up in any detailed way for the rest of the talk. Okay, so we need this Lagrangian in the symplectization, and the condition that we need is that for some very positive t's, say we have that our Lagrangian is just equal to the top Legendrian, damn it, are across the top Legendrian, and then something happens. And then it becomes just the bottom Lagrangian cross R after a certain point. Okay. All right. So this is going to be the relation that I want to study for the rest of the talk. Although of course I want to be relating it back to just the normal isotopy relation as well. And one might ask, well, why the hell do we want to study these things? So I'll try to give you three answers.
So Lagrangians, as opposed to polymorphic curves, are sufficiently flexible that you don't have to say asymptotic. You can just get equal.
Yeah, we can have them. We have them equal right on. But this is a restriction. The restriction is that you sort of can cap them off at the end. I mean, if your Lagrangian sort of comes in at the wrong angle, they're not sufficiently flexible that you can always cap them off with this cylindrical end indication. This is reducing the classical Lagrangians that. Okay, so why study them? Okay, so let me give you three reasons. Okay, so reason number one is, well, the reason you always study cobordism instead of just isotopy. Isotopy it's a very fine relation. It's really hard to get a grip on. So maybe you just want to weaken it and hope that you can get a grip on the weaker relation. And frankly, I'm saying this because I'm saying this for the graduate students in the audience, because I'm sure the more experienced people among you already know this, but I wish someone had told me this way back when I was first starting to study cobordism, because I thought, oh, it's just another relation, and then no one told me why the hell I was studying it. I'm telling you why this is why you study it. It's kind of embarrassing to admit, so don't think less of me, please. All right, so it's a weaker relation, so we hope to get a better grip on it. But let me give you some caveats. Okay, so for those of you who like to think about smooth concordance, this isn't an equivalence relation. Maybe I should say almost certainly not. Say again?
There's an example.
There's an example. Is the proof actually?
I got another job.
You got another job? Okay. Then what do you write down? This is one of those, I can't remember if the proof is done things. Yeah, the examples exist. The question is whether they've actually been proved. So it's done? Okay, so it's not an equivalence relation. Even Lagrangian concordance is not an equivalence relation. And
excuse me, is it the existence of those ends that keep it from being an equivalence relation?
well, it's not the existence of the ends. It's the fact that this is a very directional theorem. So the way you usually prove this, that smooth concordance is an equivalence relation, is you do this.
Oh, I see.
But I can't do this because it's usually the concave convex.
You can compose them. You just can't.
Yeah.
I see.
Right. I can compose them, but I can't flip them. It's the usual concave convex business in the symplectic world. It's the same type of thing. So by Ron's comment, you then think, oh, so it's a partial order, and I'm not entirely convinced I'm not entirely sure that's true either. So maybe it's partial order. The hard thing to prove is that, say, if you have a cobordism between something at the top and something at the bottom, and then you have a cobordism between one down to 2, it's not necessarily obvious that they're equal. Let me start again then. Right, so for a partial order, you need that if one's bigger than 2 and 2 is bigger than 1, then they're the same thing. But it's not entirely obvious that that's the case here. You somehow have to straighten out your cobordism, and that's not clear that you can always straighten out the cobordism.
Well, what it means is you might have an interesting equivalence relation, which is A is equivalent to B if A is less than B and B is less than A, and that might be
right. Which would be sort of
interesting.
Which would be somewhere in between.
Yeah.
Which would be somewhere in between these two relations. Right. Right. Okay, so let me just this sort. I guess the point of this is to say it's not completely understood what the hell's going on with this relation. It feels like it should be a partial order, but and maybe up to what David just said, I guess it would be by definition would be a partial order. But it's not entirely clear. Okay, so that's one. Here's the second reason. So despite David's comment earlier that Lagrangian cobordisms are not as rigid as holomorphic curves, they're still more rigid than smooth cobordisms. And maybe you can hope to solve some topological problems by looking at smooth problems by looking at Lagrangian objects. dream of every symplectic and or contact geometer who came into symplectic and contact geometry via topology as opposed to via Hamiltonian mechanics. And then the third one is that somehow Lagrangian cobordisms are the geometry underlying the TQFT structure for a lot of interesting Legendrian invariants.
Are there examples of things that are smoothly isotopic but not Lagrangian coborded?
Smoothly isotopic, not Lagrangian coborded?
Yeah.
Sure. Take the Chicano examples of 252 knots that are not Legendrian isotopic. They're also not coborded. Lagrangian coborded. Right. Oh, sorry. So right, Lagrangian cobordisms are the geometry underlying the TQFT structure of things like, say, the generating family homology, which I'll tell you about later, Legendrian contact homology, or cohomology. I like cohomology better these days for some reason. I suppose Steve just told you that it's also for the submanifold manifold stuff, or at least your previous paper did. And someday someone's going to finish off the Hagar floor business. It should also be the Hagar floor invariant should also be TQ. That's your job, right, Vera? That's your job, right?
But I'm not going to talk about it.
No, I know you're not going to talk about it, but that's your job.
I think John Baldwin actually read it.
Oh, great.
After we smoke
Is it reasonable to ask you to say a word about why you want to demand exactness for those objects?
Oh, well, I'm going to get it for. Let me give you two answers to that. In the theory that I'm going to talk about, I'm going to get it for free. So all of my Lagrangians by construction will be exact. In the contact homology business, it's the usual prevention of bubbling for holomorphic curves in order to get chain mounts out of it. Okay, so let's talk about let's go on to the second part of the talk, which it will be to discuss constructions of Lagrangian cobordisms, and sort of having to apply them to do some computations of four genera of knots in R3. By the way, again, the rest of the talk, I'm not going to talk about this part anymore, but I'll try to give you a taste of what you can do along the lines of these second two questions. So with regard to the first question, let me talk to you about constructions of Lagrangian cobordisms and the four chains. And let's begin with the result of Chantre. Okay, so let's suppose that we're working in R3. And let's also suppose that we have a Lagrangian cobordism between two Legendrian knots. Okay, these are knots now, not submanifolds. Okay, then we can relate the Thurston-Benneken at the top and at the bottom of the cobordism. In fact, the difference between the Thurston-Bennekens is simply given by the topology of Lagrangian joining them. In particular, by the way, if you have a Lagrangian concordance, that means that the Thurston-Benneken is a concordance invariant. Right, and let's call this, oh, sorry. I want to put this in a place where I'm never going to erase it. Okay, so let's just waste that board. Okay, let's just call this. Let's call that equation star. Okay. And furthermore, if I have a null cobordism, or a Lagrangian cap, if you want, then my Lagrangian actually minimizes the genus. In other words, if I confine a Lagrangian I'm actually computing the 4-ball genus of the knot. And there's some chronographer rough underlying this somewhere. Okay, and let me just reiterate. What this says is that I can, if I have a knot and I want to compute its 4-ball genus, all I have to do is find the Legendrian realization of that knot and find a Lagrangian cap of that Legendrian knot, compute its genus, and bingo, I have the 4-ball genus. That's kind of a neat. That's sort of it's something you can give to your undergrads, basically, or your really smart high school students, whichever. Okay, so
that second statement is also part of
yes, this is all one theorem. I just don't want to lose this. Yeah, this is all one theorem. By the way, this is also true. This part is also true in higher. This part isn't, but this part is well. But this part is also true in higher dimensions. That's a result of the love code, and I guess Lisa and I also did that as well. In somewhat different ways. Okay, so then with that motivation, one really should ask, so how do you go about finding one of these Lagrangian caps? Well, or cobordism in general.
But your proof is only for Legendrians that have generating functions.
Oh, yeah, so maybe I should put this in a couple of extra parentheses. Golovsky's proof is general, though. Okay, so in honor of Keiko, I will now introduce the main tool. I like that. I like that phrasing. I'm stealing it. Giving credit to stealing it. Okay, so here's a theorem, which is the main tool for constructions, and it's basically that you can do embedded surgery, and you can do embedded surgery on Lagrangian submanifolds to realize cobordisms. Okay, so here's how it goes. So let's give ourselves a disk. D inside of Rn plus 1. Remember, Rn plus 1 is where the front projections are living. Okay. So give ourselves a disk. Let's say it has no vertical tangents. And let's say that its boundary sort of gets attached to the outsides of the cusps of your Legendrian submanifold, of the front. So I guess I should draw a picture. And I'll just draw one in higher dimensions because A, I'm feeling brave, and B, it's prettier if I do it right. Okay, so there's half. Here's another. Okay, so this is all of this are just different pieces of the front at the bottom. Okay, and then I want a disk. How about a one disk? whose boundary lies on the outside of the, so it gets attached to the cusp from the outside. Right, so this is my setup. Of course, you know, if I had a nice circle of cusp, I could attach a full 2-disk D to that circle, et cetera, et cetera, et cetera. And I can do this in 17 dimensions if I like. All right, then there exists a Lagrangian Cobordism that's constructed by doing embedded surgery along the disk. At the level of the Legendrians, it's embedded surgery. At the level of the cobordism, I'm doing a handle attachment along the disk D. And let me be bold again. Okay. And here is the old disk, right? And then I'm just going to do surgery by I'll just remove a neighborhood of the boundary here. And do some nice little smoothing there. And then I'll notice that the cross-section of this puppy is just going to look like a flying saucer, like a little one knot. Again, the cross-section of 2 connecting node just looks like this. Okay. So this is the theory that you can actually do this construction, and you can do it so that you get a Lagrangian cobordism between the two. And the proof actually is just an explicit construction using generating families. And I'll tell you about those in a few days. Again, I'll have more coming about what the heck those things are. Okay, so let's see some consequences of this just for knots in 3 dimensions for a moment. So using the surgery construction, I can do the following 2 things. I can construct the following 2 cobordisms for knots in 3 dimensions. Right, well, one thing I can do is I can start with nothing and attach a 0 handle, and hey, look, I can make an unknot here. The other thing I can do just keep the color coding going, is if I have 2 cusps facing each other, I can draw the little disk between them, and I can just join the cusps together, and this gives a nice saddle cobordism. By the way, in the spirit of this non-reversibility, by the way, let me remark, you cannot flip these upside down. If you're bored, you can check that they would violate this equality. So here's some direction. You can see the directionality just in the constructions already. Okay. Well, what can you do with this? Well, I guess the answer is, I guess you can do a lot. I haven't had enough time to do nearly as much as I possibly could do, so let me just give you a small example of what you can do. Ah! Okay, I guess just as a warning to myself, instead of having this as star, okay, I'll turn it into equation number stop sign. Okay, so here's an example. Yeah, that's for me, not for you guys. I'm gonna erase it again anyway. Okay, so here's an example. So let's let okay, so let's give ourselves a Legendrian knot, and let's let say d of lambda be its TB twisted whitehead double. Then I claim that this TB twisted whitehead double always has a genus 1 Lagrangian cap. By the way, this reproves an old result of Rudolph, that as long as you're sort of below the max TB, the whitehead double will not be sliced. Okay, so how do we see this? All right, so let's. So here's our Legendrian knot. All right. Well, let's start by giving it. Let's just do one cobordism. That'll give us some little unknot along it. Yeah, I guess I didn't state this, but I will now. If you do a Legendrian isotopy, you can turn that into a Lagrangian cobordism. It takes epsilon more work than you think it does, but only epsilon. So let's do an isotopy. Well, let's see. What I'm going to do is I'm just going to drag this knot along, drag a little unknot along the pattern knot. Okay, so. Okay, so I can just do that little isotopy. Let me do a couple of Reidemeister 1 moves, here and here. Okay. And then I can just finish the job by doing a surgery along that disc and along that disc, and that will give me the TB twisted whitehead double. And that picture is a proof that these knots that these knots are not sliced. So similarly, you can imagine doing many, many more fun applications of computations. For instance, you can do this for positive zero poses of positive braids. I'm pretty sure you can do this for all alternating links and sort of do four-ball genus computations for those. And if you talk to me again in a couple of months when I'm not the chair and teaching a bunch of undergraduates, I actually might have more applications for it. All right, so let's turn to talking about the TQFT structure that you can get out of Lagrangian cobordisms. Hopefully that's sort of enough of a motivation for the more topologically minded among you. And now I'm going to turn to sort of stay much more into the Lagrangian category. Okay, so one way, so if I want to tell you about a TQFT, I should probably tell you what the invariants that I'm working with are. So one way to define some interesting invariants of Legendrian knots is via generating families. So we're going to use
Just a question about that example.
Yep.
The green curve doesn't have rotation number 0, so that means it doesn't have a generating family, right?
Right, that's correct.
But the white curve does have a generating family?
The white curve does have a generating, yeah, so let me be careful about not, until this point, I don't care about generating families. My construct has nothing to do with generating families, except the proof uses them, but it only uses them locally.
Oh.
So I wasn't lying to you by not using the word generating family in statements before. This construction it's exact. I mean, it's exact, but it's not. There's no generating families yet. That'll come in probably this morning again. Okay. Right. So I want to use this idea of a generating family to construct some non-classical invariants. And since I'm sure that all of you absorbed and have memorized what Brad told you on Thursday morning, I clearly can just let me remind you what the hell Brad told you. Okay, so here's a reminder / summary / slightly different perspective on what Brad did. Okay, so here's a good way to produce Legendrian curves. Well, a good way to produce Legendrian curves, or if you want sort of Legendrian sheets in higher dimensions, is just to use the one jet of a function. I'm slowly killing your shark. Sorry, Vera. Okay, so if I have a function f, do it this way. So if I have a function f from Rn to R, well, it's one jet. It's the object that takes in an x and spits out an x, the derivative of f at x, and the function value. Now the first two things give you a Lagrangian in R2n. Let's do that in Lagrangian R2n, and remember R2n is just the cotangent bundle of Rn. That's the right way to think about it. And then the whole thing gives you a Legendrian in R2n plus 1, which of course is just a one jet of Rn. Okay, so you can imagine, and then the front projection is certainly just the x f of x, and then, as we said before, the y coordinate is usually just the derivative of the slope in the xc plane. So this is sort of recovering the old front pictures, but this is, if you want, for those of you who come from the age where people used to write down that the standard concept structure was dz plus xdy, this is why that's wrong. I mean, it's correct, but morally wrong. Somehow the dz minus y dx is sort of the right setup. Is sort of the right setup for the one jet, for thinking about R3 as the one jet space of R. Okay. However, in R3, you'll notice the problem with this is that, well, you can only get graphs. It's kind of hard to get knots. So it's made to get compact objects. We should do something a little bit more tricky. And what we'll do is we'll extend the domain. We'll extend the domain of our function f. Okay, so we'll think of f now as a function from Rn across some possibly very, very large Euclidean space to R. And instead of trying to graph that, because that wouldn't be in R, that wouldn't be in Rn plus 1 anymore. So instead of graphing it, what we'll do is we'll think about f as a family of functions on our big N parameterized by the x's in R little n. functions, and then we'll just take its surf diagram. In other words, sort of the graph, or just plotting the critical values of these functions as invariant x. Okay, and that surf diagram is precisely is the front for a Legendrian submanifold. By the way, let me say one thing. You can't just use any f, right? Somehow you have to have these things be somehow not degenerate. And the other thing is, if you want to, we eventually want to do Morse theory on these things. And Morse theory on non-compact domains is not particularly fun. So you want to pretend like you're doing Morse theory on a compact domain. And the way to do that is just to specify some behavior of infinity. So let's, for instance, specify that these things are, say, linear outside of a compact set. Okay, so that lets you pretend to do Morse, pretend to do sort of compactly supported Morse theory, even though your domains are in no way, shape, or form compact.
Can you just write down in that, how exactly is that a generalization of this?
How is
take a left on an F from your left-hand board, and what's the F in your next board?
It's exactly
capital N. Capital N.
0.
I see it's a good point. Okay.
Yeah.
0.
Or if you want n equals 1, then just sort of add on take f plus a quadratic in the other variable element. I'm not trying to be flip.
I understand.
Yeah. Okay. By the way, I should note. By the way, this is a really cool construction because now, by the way, it lets us analyze Legendrian submanifolds using techniques of finite dimensional Morse theory instead of that really nasty analysis that scares the crap out of me. But there's one penalty you pay. Is that not every Legendrian has a generating family. Of course, then which ones have a generating family is in itself a very interesting question. It's actually very tightly related to, for instance, when the Legendrian contact homology has an augmentation. In fact, those two are equivalent in dimension 3 and should be equivalent in higher dimensions as well. Okay, by the way, so this is how to get a generating family for a Legendrian submanifold. What about Lagrangian? What about a Lagrangian Cobordism? So you can also do this for Lagrangian Cobordism because of the following cute little miracle, is that the symplectization is actually symplectomorphic to the cotangent bundle of, say, the positive reals cross Ra. So now, since we're in a cotangent bundle situation, we can once again apply the generating family technology. And that cylindrical at infinity condition becomes the following. Well, if we have some generating family for the Lagrangian cobordism, well, we say that sort of as long as sort of t is away from some compact interval, we just have our generating family for the Lagrangian just be the generating family for the Legendrians multiplied by t, and that sort of gives you that cylindrical / conical behavior outside of a compact interval. If you're really bored, you can check that this does what you think it should. Okay, so let's try to figure out how to get some invariants out of this. Well, we're not going to work directly with the generated family itself. Instead, we'll work with something called the difference function, which just takes the generating family, works on sort of some kind of final product of its domain, and just takes the difference of the generating family with itself. And the nice thing about this difference function is it's very easy to compute that the critical points with positive critical value are in one-to-one correspondence with the rank chords of the Lagrangian submanifold. And for you contact homology / Floor theoretic people out there, you think, ah, this is good. This is how you this is how you start creating some kind of Floor theory. And you want to think about what I'm about to do as some kind of finite dimensional approximation of some Floor theory. Okay. All right. So let's just define. Let's say the generating family cohomology. I'll just write of f because the function already encodes the Legendrian. Well, let's just let that be the cohomology with some nice little gradient shift to keep things nice of the sublevel set of the difference function sort of way up top relative to the sublevel set of the difference function sort of just over 0, so there's no critical points between 0 and epsilon. And then, if you want an actual Legendrian invariant, you sort of have to take the set of all of these generated family homologies over sort of the set of all possible generated families for the given Legendrian. And if that sounds awful, those of you who work in the contact homology world, you have to think, if you look at all the linearized contact, if you want to get an invariant out of linearized contact homology, you have to sort of take the set of all linearized contact homologies over all possible augmentations of the Legendrian contact homology. This is to get an invariant, you're doing essentially, well, actually quite literally, by a result of Dan Rutherford and Dimitri Fuchs, quite literally the same thing. They proved that in R3 at least, given one of these generated family cohomologies, it is isomorphic to a linearized Legendrian contact homology group for some augmentation related to the generating family. So actually related to. Since you're in the audience, Dan, you get your name on the board. Thanks. Okay, so there's the invariant. How do we get it? How does this fit into some kind of TQFT structure? Do you want me to rewrite those names, Will?
No, I was asking him, what is the cohomology group you have written on the right?
Oh, so this is the, so let's take the sublevel set of the difference function at some level that's higher than all of the critical values.
Oh, that's ordinary cohomology.
Plain old cohomology.
I see.
How about Morse cohomology?
Yeah.
Yeah, plain old cohomology. Okay, so to get a TQFT structure out of this, what I'd like to do is I'd like to take equation stop sign, and if you allow me some fun language to categorify it. Okay, this is a theorem that Lisa and I proved. And so let's suppose that two Legendrians are related by a generating family compatible, and now I'm including this line. Before I was not, but now I am. Generating family compatible Lagrangian Cobordism. Then there exists a long exact sequence. Okay.
just means you're generating family for lambda minus lambda. The Lagrangian is made by a one-parameter family going from the one generating family to the other.
Right, so then I have a long exact sequence that relates the generating family cohomology at the negative end to the generating family cohomology at the positive end. And let's call this map sort of, this is the TQFT map. And there's an error term that comes from the relative cohomology of the Lagrangian itself, and this is just the ordinary old, singular, Morse, whatever you like, relative cohomology of Lagrangian, say, relative to the top end. And here are two immediate and quite fun corollaries. So first of all, if you have a concordance, then this cohomology group vanishes, and it shows that the generating family cohomology is a concordance invariant. Okay, so if you get some mileage out of eliminating one cohomology group, let's try to eliminate another. So if we have a null cobordism, let's see, so if you have a null cobordism, that means this guy vanishes, and so we have an isomorphism between the generating family cohomology and the singular cohomology of the cat. And I guess what's cool about that is, my goodness, this is some strange non-classical Legendrian invariant, but now we have a geometric interpretation. And for those of you who like these kinds of structures, like me, you can there's some kind of duality that you can define on the generating family cohomology. This is my own favorite hobby horse because this is my favorite theorem that I've ever proved. So, it's actually exactly the same as Poincare duality on the cat. So somehow the duality here explains some otherwise mysterious duality up here. Okay. And an interesting aspect of this theorem, beyond these two quite nice, if you ask me, immediate corollaries, is that we can now use it to go back and look a little bit about the Legendrian isotopy question. Okay. Let's in contrast to what Tom did, instead of talking about geography, we can talk about botany. Although, if I talk fast enough, I'll get to geography too. Maybe we'll get to geography too. We can actually talk about the botany of Legendrian submanifolds. And we can do this in the following way. So if you combine this long exact sequence with the earlier surgery theorem, you realize that this long exact sequence is not quite as nice as in these cases, but is very easy. Because if you do a surgery, i.e. attach a handle, this is only non-zero in a single degree, right? So that means it's relatively easy to compute this generating family cohomology for something that you get from surgery, or even better, repeated surgeries, right? So if you combine that aspect with the surgery theorem, we can make the following computation. So let's consider the following Legendrian submanifold. And by the way, I'm doing this in higher dimensions because I have to do it in higher dimensions. The theorem I'll tell you at the end is just simply not true in R3. Okay, so let's take this. This is a so think about this as a generalization of a Hopf link. Okay? So just take a flat saucer, take another flat saucer, sort of link them at their top and the bottom. And then let me take. I'm just going to draw. I'm just going to draw this a little bit more sketchily than it should be drawn. But sort of now take sort of spun versions of these Reiter-Master 1 moves going down. And then maybe at the bottom, we'll just take the bottom and just pull it around. I have an extra dimension to play with, so I can do this. Pull it around and sort of put it up next to here. Okay, where the cross sections here are all unnotched, and that's supposed to be nice and flat here. There, much better. Okay, and then we can do a little we can do a nice little surgery there, right? And let's call the resulting submanifold. Let's call the resulting submanifold lambda. And by the way, I can certainly do some higher dimensions as well. Okay, so the construction theorem tells me that I can do this. This long exact sequence tells me that its generating family cohomology is Z in degree, say, k, n minus k minus 1, and degree n, and degree 0 otherwise. By the way, that k is coming from the difference in the Morse index of sort of the critical points that make up these two components of the Hopf link originally. Okay. Well, that's nice. So in particular, I have a nice infinite family of these things, right? And if I take one of these things and just connect some on, do another one of these surgeries to any Legendrian submanifold that I have, I immediately produce an infinite family of non-Legendrian isotopic Legendrian submanifolds. Well, that Legendrian submanifold better have a generating family, and this gives me an infinite, and this gives me an infinite family of non-isotopic Legendrian submanifolds. And before you pounce, Mr. Sullivan, this is just this is an early result of Nair, Echo and Nair. Sullivan, they proved it using slightly different techniques, and they didn't write this down, but it's in there.
Okay, I don't remember that though.
It's in your paper, Mike, I promise.
I actually have another question though.
Yeah.
Kind of goes back a slide though.
Damn it.
The epsilon, the augmentation from Fuchs Rutherford.
This epsilon and this epsilon have nothing to do with each other.
Right, yeah.
Hang on.
No, I'm like thinking of that as a Lagrangian filling, right?
Yes.
And so,
Yes.
can I say anything about the generating?
Yeah. So, for instance, what you can prove is that if your Legendrian has a generating family, then there exists an immersed Lagrangian filling. I don't know about embedded, but there at least exists an immersed one. And it's probably nicely enough immersed to do well enough for an augmentation. There should be a relationship between the two. And if you call Frederic in about 6 months to a year, they'll tell you that that's actually true. I shouldn't have said that. Don't call Frederic, and don't tell myself that.
Can I ask a peanut gallery kind of question for non-experts here? So these are all two spheres, right? So
Sure.
Does the difference in Morse index, does that have anything to do with their embedding type as a smooth submanifold? Or is that,
No.
so these are all like isotopic as smooth spheres, is that right?
Yes, that is true. That is true. Well, in fact, they better be, because these are 2 spheres in R5. Or in
I
general,
see.
n spheres.
I see, they're less, yeah.
So there's no
Yeah.
there's no topological
Yeah,
knotting anymore. But which is kind of interesting. There's no topological knotting, but there's tons of Legendrian
Yeah,
knotting,
yeah.
right? This Morse index is really coming from, these are really critical points of the generating family, and it's just literally the difference in the index of the critical points. Okay, so let me finish with one quick remark. If you soup this up, and if you want to talk about geography instead of botany, for instance, if you soup up this construction a little bit, you can actually figure out that you can obtain any generating family cohomology. You can find an example of a Legendrian submanifold that contains basically any generating family cohomology you want, as long as it obeys some kind of duality. That implicitly answers a question that, well, I guess that I asked myself long ago. So, why do you guys care? Because it's actually kind of a cool result. And then, finally, this should be a beginning. This isn't a summary talk of a long-developed field. This is the beginnings of a field that we don't know a huge amount about. And hopefully, I've given you guys some tools that you can use to think about both applications of Lagrangian cobordism, both within the world of contact and symplectic homology. Forget the homology word. Contact and symplectic geometry. And you should also think of in terms of applications to the smooth world. So, thanks very much. I have a question for myself. Hey Josh, why didn't you thank the organizers? Because I'm an idiot. Thank you very, very much to the organizers for A, for the invitation, and B, for such a inviting such a wonderful set of talks before me, and hopefully tomorrow as well. So, sorry. Real questions?
I just do have questions. I think the thing I mentioned about here is also a very complex too.
Yeah, well,
Yeah.
about Haverford, you mean?
Mm-hmm.
Yeah, it's in progress.
Okay.
Don't want to say it's a theorem yet.
And also that example that shows it's not that's also you or Baptiste or
Yes, that is.
is Baptiste, right? Is he? I thought he needs. Oh crap! All right, so here's another really big thing that I forgot. So this theory is also parallel to some work of Ekholm, Honda, and Kalman that should appear this summer, and Baptiste's work is dependent on theirs.
Oh.
Baptiste's work is dependent on theirs, but assuming that theirs works and it's going to work, then Baptiste does have that example.
What's next speaker?